Yes, one of the problems that we're going to solve is the fact that is the demand for bandwidth goes up, and along with capacity, you get this situation where you can't really do flash. It's extremely expensive because of the capacity considerations. Bandwidth considerations takes a lot of spinning disks to get the bandwidth up. So why not try basically a hybrid solution? And in doing a hybrid solution, you go from a traditional situation where you have your CPU memory storage to CPU, possibly near memory, far memory, which is still on the same node, to a situation where you have near storage, which is SSD based, and then eventually to your spinning disk. And of course, the initial implementation for this near storage actually came from the labs for something for a bus buffer. From a hardware perspective, basically you got DataWarp and software-defined storage. It's your high-performance storage. In the case of CRAY, our spinning disk is the Synexion. That's our Lustre solution, and that's our scalable file system. And so basically, you would then use the DataWarp as your bandwidth component, and the Synexion as your storage component. And that, basically, in this particular model of CPU, near memory, far memory, with near storage, of course, the DataWarp would fulfill the near storage, and the far storage, of course, Synexion or possibly DDM. With the environment, of course, we have our Synexion. If you wanted to try to do large capacity, large bandwidth situations with Synexion, and of course the CRAY storage component, or you can use this blended solution, mixing DataWarp and Synexion. Some of the simulations we've done, looking at the costs and that, and depending on the situation, we've seen the possibility of savings of up to 40% on storage by using a product like DataWarp. From a hardware perspective, currently DataWarp is just on a CRAY XE system. It's actually on an XE IO node, which is an Intel server. The SSD component, currently we're using an Intel P3608, pair of NVMe SSDs. It's on what we call our Aries internal network. From a software perspective, we basically virtualize put this virtualization layer above the hardware, and which gives us a single solution for both flash and your spinning disk, and it's an automated move policy, moving data to and from the storage. The phases of DataWarp so far, our initial phase was basically nothing more than mounting a file system that was basically coming off the DataWarp SSDs. Now with phase one, which we currently are in, we can dynamically allocate and configure the DataWarp using the workload manager. We still got some somewhat explicit movement of data between DataWarp and the parallel file system. We use these stage in, stage out components. But we do have the capability of striping across the range of DataWarp nodes. Now phase two will introduce DBS client caching, where DBS is actually the layer that we move data between the nodes with, which is really underneath the covers. It's actually elegant, so we kind of cheat there. And there's implicit movements of data between DataWarp and the parallel file system. If you're not familiar with the CRAY XE system, what we have is a series of compute nodes, all integrated with Aries interconnect. Off the Aries also is connected DataWarp nodes, which has a pair of SSDs. And in this case, our default's about 3.2 terabyte SSDs, 6.4 terabytes per node. And so as data comes from the compute nodes to the Aries networks to the DataWarp, eventually, if you need the data moved, or the user requires the data be moved to Lustre storage, it goes back to the Aries through Elnet routers and then to the remote storage. From a user perspective, as I mentioned, he talks to the workload manager, who then talks to the DataWarp services. And the application in parallel file system uses the data virtualization service, which is DVS. If you ever hear the term DVS, that's what it is. And that sits above this thing called a DataWarp, for lack of a better term, DataWarp file system, which then talks to the underlying file system, which I believe is XFS. And of course you have the volume manager and the physical devices, which in this case is Intel SSDs. That's a little simple automation. There we go. From a user perspective, there's a couple of different ways you can access it. A new user could just use it. Transparent, he doesn't have to do much, he doesn't have to have much experience, but he can take advantage of it. From a more experienced user, he can actually make modifications and add commands to the workload manager to do additional features. And then, of course, a power user can actually interface it using CLI. So what an engineer basically does, he just needs to know about how much space he wants out of the DataWarp pool. Is it shared or is it private? Do I eventually, when I'm done, write things out to the parallel file system? And he does all this through a workload manager job script. Currently, Slurm, Moab, Torque, and PBS Pro are the current workload managers that are interfacing with DataWarp. There's no reason others can't. It wouldn't be that much of an effort to include other workload managers. There are various use cases for DataWarp. The initial item I'll talk about is the shared area, where you basically have, you can do it in a couple of different manners. You can use, if all the compute nodes in a group need to talk to or read one particular area, you can cache the data on a DataWarp node, and then all the nodes can read that information out of that DataWarp node. You can use it as a sharing area for as one compute node writes the information to it, then another compute node can read the information from it. Or you can actually use it as a performance scratch area, where you take a group of DataWarp nodes, create a strike group of it, and the compute node jobs all read and write from that scratch area. Some other use cases, of course, the local storage burst buffer, which was the original intent, and the parallel file system cache. The initial burst buffer configuration, what the intent was, a situation where you had a lot of compute nodes that needed to checkpoint memory, and they needed to do it fast, and then return control back to the compute nodes. And then as it's going through its iteration of compute interval again, then from the DataWarp nodes through the areas out to the LNS, you would then basically trickle sync information out to the Lustre storage area. And I've already talked about the shared storage area, in this case using a series of DataWarp nodes in a parallel configuration being read and written from a group of compute nodes. As local storage, you could actually use it as each individual compute node could have it as its own private little work area, or even a swap area. So you can, there's multiple ways that you can use it. And finally, what we're working toward is having an option for a parallel file system cache, and such that as users write their data out, it actually goes to the DataWarp node first, and then it gets trickle synced out to the file system. Some examples of configuring a job with DataWarp. Basically, you request DataWarp services, you specify how much capacity you think you're going to need, and that's kind of key to the number of DataWarp nodes that get allocated. The administrator will assign a particular granularity to DataWarp. So if you have multiples of those components of granularity, you end up with multiple DataWarp nodes. Then you define what type of storage you wanted to use, whether it's scratch or cache, or however you want to actually use it. Then you specify also the access mode, whether it's striped, where all compute nodes see the same file system, and you're using all the DataWarp nodes, which of course the end result is you're hoping to not only end up with additional capacity, but also bandwidth. Or you can specify a private mode, in which case each compute node sees, in essence, a different file system. Or you can have a mixed mode, where you actually end up with two different mount points. So you have your own private area and a striped area. Here's an example of how you would actually use it using Moab. In this particular thing, you have a DataWarp definition. You say type is scratch, my access mode is striped, capacity in this case is 790 gigabytes, which most likely was probably on one DataWarp node. There's a command in there, dwstat, that would actually show you which your space would be available. In this particular case, the user specified that he wanted to see how much space he really got. And then you basically specify the location of where you want your output to be run. Here's an example of a run using it for scratch and as cache. The main difference is you specify type equals scratch. The PFS basically says where is my information located, and then what will happen is the DataWarp services actually return a pointer that you use when you read and write, so it then goes to the appropriate DataWarp nodes and then eventually out to the file system. As far as the bandwidth, how it performs, it depends, of course, on transfer size, the number of streams per DataWarp server, the number of DataWarp nodes, obviously, and because of the way it does its striping across there, is there any other activity that happen to also be happening on the DataWarp node at the same time? One of the main goals of using something like a flash storage like DataWarp is to take this particular yellow time step that's being caused by the I/O and shrinking it down. So the goal is to reduce the time, the I/O to wait time, and decrease the actual runtime of the job. Here's an example from MSC NASTRAN where the job was doing various types of reads, and some of the reads were causing long wait times. And we're using a device like DataWarp, we're able to decrease that wait time and reduce the wall clock time of the job. By 2x in this case. Here's another example using Abacus. Lines of interest, of course, are the bottom two, the red and the purple. The CS400 is basically just a CRAY cluster, and they were comparing it against writing to local temp and then also on an XC board system, writing it to DataWarp. So the end result was the wall clock time was less in the jobs using DataWarp. Some considerations when trying to figure out is DataWarp something that is a possibility to use. Most of these are kind of common. Know your workload, your I/O workload. What is your capacity requirement? What's your bandwidth requirement? What's the interval between when the job writes data, and then returns, or the time between I/O intervals? And from that, you can basically look to see how you can calculate what percentage of the bandwidth do I want DataWarp to be responsible for versus spinning disk. So that percentage of capacity needs to be in there worth of something like DataWarp. And depending on the I/O interval, do I need to assign excess bandwidth to some flash like DataWarp in order to handle both the incoming data from being written from the compute nodes and the data gets written out to the spinning disk. And of course, the consideration is budget. Yes, the bottom line is it's basically all about reducing your time to solution and hopefully reducing the cost of the time to solution. QC is more of one of our marketing slides, but anyhow, yeah, DataWarp, faster time to insight, easy to use, dynamic, flexible.